Okay, so for f of something like f of x equals x plus 3 squared, we can do the product rule, or we can expand it out, and we know that x plus 3 times x plus 3, isn't that x squared plus 6x plus 9? Oh, now I could take the derivative, and what is that? Yeah, it doesn't matter which method you use. If you do it correctly, you're going to get the same answer. That's all fine and dandy. But what if I want x plus 3 to the 10th? So the power rule only applies if it's a single term. You can't just, we're going to use that idea though. Yeah, we're going to use chain. We're going to use something called the chain rule, which allows us to use our power rule. Now again, everybody does chain rule a little bit differently in notation. The notation I like to use is the notation that I think comes in handy when you do integration, but I'm going to write both of them out for you. So we're going to come back to that. Let me give you the definition of the chain rule so you can kind of understand where it comes from. It's theorem 1.3.13. It is a theorem. It's called the chain rule theorem. And so we're going to write out the formal definition so you have it. And then we're going to start to apply it in a bunch of examples, and then you will get it. You may not get it with the formal definition theorem, but that's okay. So let's start. Suppose y just go with it. Suppose y equals f of u. And it is differentiable at u equaling some function g of x. And u equaling g of x is differentiable at x. All right, so we got all the boring stuff out of the way. It all has to be differentiable at all these different places in order for this to work. That's going to be given to you. All right, you don't need to worry so much about that. The composite function so now what am I going to do? I'm going to replace u with my g of x. Do you remember these are from pre-calc, composite functions? That's a function inside a function. The composite function is differentiable at x. And we can do the derivative two different ways. And we can express the derivative the following ways. Sorry. All right, we're going to express the derivative two ways. The first way is my preferred method. It's using dy dx. Derivative of my original y function, which is what that was, in relation to x. Well, what that means is I'm going to take y in relation to u, and I'm going to multiply the derivative of u in relation to x. Okay, so these are just notations you're going to get used to. Same thing. These are equal. These are the exact same thing, just a different notation. The other notation is using your f's and g's. d dx of f of g of x equals f prime of g of x times g prime of x. Again, I like this one better because I think this is the one that helps you in the future. That's why I like to use it. All right, so let's go back to that function I wanted to do. That function I wanted to do was x plus 3 to the 10th power. And let's see how this theorem can apply to that function. The key with using the chain rule is identifying the composite functions, the function inside another function. So you've got an outer thing that's happening here. Something's being taken to the 10th power, right? And if that something was a single variable, we could just use what we know, our power rule, correct? Does that make sense? But that something's not a single variable, but we get to do anything we want in math. Let's make it a single variable, and I'm going to use u. So what I'm going to say now is I'm going to recognize if my outer function is raising to the 10th power, my inner function is simply x plus 3. Does everybody see that? Think of something being raised to the 10th as the outer function. The inner function is just x plus 3. And I'm going to let u be equal to the inner function. So I'm going to say, okay, first thing, identify the inner function. Actually, let me write that down for you. First step, identify inner function. Identify inner function. In this case, and set equal to u. So u equals x plus 3. See that? Rewrite with u. So x plus 3 to the 10th simply becomes u to the 10th. If you can do that part, you're like 3/4 of the way there being able to apply the chain rule. So what did the chain rule say? So I'm going to let this be y, just to identify some things. I'm going to let that be y. Chain rule says, if I need, so step 3, I'll say apply chain rule. And what's the chain? Well, I want dy dx, and that's going to be equal to, come back up here, dy du and I like this for a lot of reasons. Let's stop and look at this for a second. Why does dy dx equals dy du over du dx? Think algebra, right here on me. They cancel, right? Does everybody see it? So that's what's so cool about this. And that's why I like this notation, because it starts to introduce you to the dy dx stuff, which is something you need to start getting used to anyway. So yeah, this works because the du's technically cancel away. So at the ultimately, all I'm finding is dy dx, which is what I want. I want dy dx. But I'm doing it in pieces, and watch how nice and neat these pieces now are. So I need each piece. Let's start with dy du. So my y, which was x plus 3 to the 10th, is now u to the 10th. So dy with respect to u, if y is u to the 10th, so what's the difference between dy dx and dy du? It's the variable we're using, right? This dy this is now done with respect to u. So that means I can come over here and just apply my power rule. What's my power rule say? What's dy du? If y equals u to the 10th, what's dy du? 10 u to the, that part's done. But now, that's dy du. I did that. Now I need du dx. And yeah, I'm going through a lot of steps where you're not going to have to do all these steps. I'm just doing it because it's the first time you're doing this, okay? Now I need du dx. Oh, well, what was u? U was x plus 3. So what does that mean, du dx? I want the derivative of this u with respect to x. So all I'm doing is taking the derivative of x plus 3. And what's the derivative of x plus 3, everybody? 1. This was a horrible example for that reason. All right, which means we're going to quickly follow it up with not so horrible an example. All right. So, dy dx is simply my 10 u to the 9th times 1. And the last step is get rid of the u. Replace your u. So what was u equal to? X plus 3. That is such a horrible example. So we're going to really quickly, and the only reason why it's a horrible example is because you think, well, I can just apply the power rule like I said in the first place, right? Okay, so let's jump into example 2 super fast. Take that to the 10th power. Ah. Yes. Minus 7. Let's do that. Should be a 7. There you go. I'm not going to go through all those steps this time, but I am going to do, what would I write down, me personally, if I was doing this problem? I'd identify u. So I go, okay, if y equals that, my u is the inner function. So what's my entire u this time? 3x squared plus 5x minus 7. I personally would quickly follow up with finding the derivative of that because I know I'm going to need it. Does that make sense? Oh, so what's the derivative of u with respect to x? I'm just going to do that since I know I'm going to need it. What does that come out to? 6x plus 5. All right, cool. That's over there. Now off to the side, I'm going to actually do the problem. Well, if u equals that, that means it's u to the 10th power, which we already know we can take the derivative of. What's u to the 10th power? All right, so this is my, this is my y, so that's dy du. So but you gotta multiply them together, right? So it's 10 u to the 9th times 6x plus 5. And then you gotta make sure there's no u's left in the problem. There it is. There's your answer. There's your derivative. We can call that y prime. You can call that dy dx. You can call that whatever you want to call it, y prime or dy dx. What you'll get in the habit of recognizing after you, so here's the trick. If you're not getting the answers right, I expect you to draw all this out, right? Sometimes you need to do that a few times. But then, as you start to recognize these problems, or they're going to get way more complicated, you'll start to see that example 3, I'll kind of show you my thought process sometimes, is just you're going to get good at this, I promise you. And where the chain rule comes in and where you can get really good at it, is to be like, all right, I recognize the inner function. I know I got to bring the 6 out front. I know it's that function to the 5th power, but now I need to multiply it by the derivative of the inner function, which is, and see how quick that really can be. So this is as you're learning it, and as the problem gets really complicated. Sometimes they're really complicated. I will work this out. But if they're ones you recognize, you're getting the pattern down of, okay, I can apply the rules I know, but then I got to remember to attach the derivative of the inner function. That's the chain rule. And it's called a chain because sometimes this happens multiple times. I won't get you with that one just yet. But let's get away from this something raised to a power, and let's just go through a few examples, okay? A few quick ones. Because again, you got to recognize the inner function. And sometimes finding the derivative of that outer function requires you to put it in terms of u because it becomes too complicated. So we're going to go back to using our u's. So again, first step, what's my inner function? What should I let u equal? Yeah, that's it. So then y becomes the square root of u. And by doing it this way, you know you've got to find the derivative of each. Just underneath of it, like I would write it out this way. Here's my u, rewrite y next to it, find the derivatives of each directly underneath. So let's find the derivatives of each. So this is du with respect to x is 10x, right? And then I want y with respect to u. Well, let me change the algebra on that one. Instead of making it a radical, I'm going to make it u to what power, everybody? Yeah. So when I take the derivative of u to the half, it becomes 1/2 out here, correct? And what's 1/2 minus 1? -1/2. Let's clean that up so I know what it looks like. Isn't that 1/2 radical u? So again, you have your u, you got your y, derivative of each then you bring them together. Okay? Then you need to bring them together. So the ultimate I always start with this one, though. I don't know why I don't put that one. Well, you have to put that one. I always reverse it. So 1 over. Now, as you're writing it, do you recognize you don't write the u anymore? So we can get rid of that, right? As I'm writing it, it's not 1 over 2 radical u. What is u? Don't forget what u actually is. And what am I multiplying it by? Yeah, which is the derivative of what's inside, 10x. I don't like it there. I'm just going to put my 10x right there. Right? Isn't that it? There's my 10x. And this never seems that bad. Until it all starts to get put together. So we're gonna do a few more. What was that? Number 4? All right, number 5. I can use the chain rule on this. I can definitely use the chain rule on this. But you got to recognize first to use the chain rule, what's the inner function? This is always the hardest thing to remember. What's the inner function? What's the tiniest part of the function? What's the big function? And then what's the little function? In this case, it actually is little. 5x. The little function's 5x. So y becomes, oh, e to the u. What's a derivative of 5x? What's a derivative of e to the x? Do you remember that one? Yeah. Oh, it's a u. E to the u. Oh, there's my answer. That's it. This one, I'm actually going to write the u part first because it makes sense. So when you're looking at these, you just kind of need to look at them and say, what makes sense to write first? I'm going to put the 5 first because that makes sense because you don't put e to something and then a 5 after it, right? So my dy dx becomes 5e, but I'm not going to write it as e to the u because I don't care about e to the u. I want it as e to the what? There. That's the idea. That's where chain rule comes in. Trig function. Example 6. Let's do tan of 3x minus 5. What's u? Yeah, you're good. So I'm doing these very specifically so you get in the habit of recognizing your u value. So then y is just tan of u. Derivative of each with respect to x is 3. Yes. Remember, I told you got to memorize those. I gave you all the trig functions and said it's up to you now. You just got to memorize them all. Secant squared. Write them together. So derivative of y with respect to x is 3 secant squared, not u. Done. Yeah, unfortunately, these get really hard. Are you feeling good about it right now, though? Feeling pretty good about it right now? I hope. I want a couple different things that. All right. So here's the thing. We've done problems that's just a single chain rule. There are problems where you have to apply the chain rule a couple times. There are problems where you have to apply the chain rule within a product rule. Chain rule within a quotient rule. So there's a lot of different layers to this. Let's try one next where it's maybe doubled, right? Chain rule, chain rule. They get a little confusing. Sample 7. But I'm looking at the book and yeah, this one definitely looks like one of them. So, number 1, do you see multiple functions here? So the sign itself, the big outer function is sine to the 5th power, right? Something to the 5th power. But we also have a cosine function. But that cosine isn't just a plain old x. Do you see that? So we can break it up and we can do different things with it. If we were to break it up, looking at the big function, the sine to the 5th, you'll get so good at this, you'll just like jot it down. Promise. We have sine to the 5th. Everybody see that? So what do you think you want to make u first? Cosine 3x? I think first, let's break that down. Understanding we're probably going to have to break down cosine of 3x. All right? Does that make sense? But we can do that. So if we said, all right, there's no right or wrong here. You can approach this different ways and still get the same answer. If I let u be cosine 3x, right, then y becomes sine to the 5th power of u. To do that, I have to, this one's actually like 4 chain rules, believe it or not, because to get du dx, wouldn't I have another u here? I have another embedded function here. But we can do that one. Because that would be, what is the derivative of cosine number 1? So let's suppose I pretended this was just cosine of another u. What's the derivative of cosine, everybody? Negative sine, right? So, okay, it's going to be negative sine of 3x, but then I have to multiply it by the derivative of the inner function, and what's the derivative of 3x? So wouldn't that be times 3? So I actually applied the chain rule while I was getting this derivative. So du dx actually becomes -3 sine 3x. And if you don't believe me, you can go ahead, you let u equal 3x, what's the derivative becomes 3. So this is a chain rule within that u. But we have that one done. Du dx is definitely -3 sine 3x. Now, sine fifth to the u. Trig functions are funny because this is the same as that. Remember that? And if I think of this as a basic power rule, what's anything raised to the fifth power? How do I get the derivative of that? Isn't that 5 sine, and that would be to the, right, because let's pretend, let's let, I'll pick a different, I don't want to keep using u's because I don't want to confuse you with all the u's, so let's pick q. If q equaled sine u, it would be q to the fifth power. And isn't q to the derivative of q to the fifth power is 5q to the fourth power, right? So this becomes 5 sine to the fourth of u. But then I need the derivative of sine u. And what's the derivative of sine u, everybody? Because it's a chain rule. So I need the derivative of the inner function. What's the derivative of sine? Cosine u. And then you got to put everything together but replace the u's. So let's bring it all together. It's crazy. You got to put this with that. And replace my u's. So we have, well, -3 and 5 is just -15. I lost it. No. It's back. All right. And then I have a sine 3x. I already used the 5 and the 3. I have a sine to the fourth. What was u, though? And what was u again? Okay, that is one of the craziest problems you'll ever get to. Because that one actually had, when we broke it up, we had to use the chain rule in each area we broke up. So you had like 3 chain rules going on. You had one in each area and then the big chain rule. That's crazy, isn't it? It's crazy. I always like try to challenge myself to see if I can just do it in my head. But I always screw up because when I look at it, I say, okay, so there's going to be a 5 and then a sine of cosine 3x, and then that'll be to the fourth power, but then I need a derivative of cosine 3x is sine 3x, and then I usually lose it and forget where to go, so I always have to write it down. But if you looked at it separately and you broke it down like that, you simply just have your, if you know, breaking it down lets you look at, okay, this one over here, yeah, it's a chain rule, but it's a manageable chain rule. And then this one over here, yeah, it's a chain rule, but it's a manageable chain rule. And then you bring them together in the end. Just don't forget to bring them together at the end. And then, of course, you could end up with that was long. Here we go. Last one. And then I'm going to let you get together with your labs. Last example. So the biggest thing is when you approach any function you need to take the derivative of, you've got to look at it and say, how do I start it? You now know product rule, chain rule, quotient rule. When you see this, what's going on? You've got an x and an e to the 7x. They both have an x in them. They're being multiplied together. What do you think the first thing is that you should recognize? Product, right? You have product. You will use the chain rule in there when you're finding the derivative of part of that product, but overall, that is a product rule problem. Okay? So when you're taking the product rule, and what did we start with taking the derivative of the first one? It doesn't matter because product rule is, commutative. You can go in either direction with product rule. But so if we start, take the derivative of x. What's the derivative of x, everybody? Copy the next function down. Plus, copy the first function down. What's the derivative of e to the 7x? That is a chain rule, but it's a really easy chain rule, right? Because the derivative of e to the x is simply e to the 7x. But you need the derivative of the 7x. And what's derivative of 7x? Times 7. So ultimately, in the most simplistic form, that's what your chain rule is. Take the derivative of the whole, and then take the derivative of the inner function. The derivative of the whole is just e to the 7x, and then the derivative of the inner function is 7. And you just clean it up and you're done. So, okay, I gave you an easy one. Because a lot of times you see those e's and you're like, oh my god, this one's going to be hard. They tend not to be. So it's just e. You can leave it like that. I mean, if you really want to do this, it's 1 plus 7x. That doesn't matter. That doesn't really do anything. So you will have to apply your chain rule, your quotient rule, embedded within others. If you have a big quotient raised to the 10th power, right? Yeah, you put the 10 out front. You have that big quotient now raised to the 9th power, but you need the derivative of that big quotient then. All right? That's chain rule. It's just constantly doing all these little pieces. So I'm going to stop there today.